Hi everyone. So I thought I'd give you a little primer on error analysis for this lab class. So we're going to take a look at the data for Lab 2. And this is the data that you were given to do analysis on. You can see it's just a little spaced out here, but it's just a whole big long column that goes down to here. And then the linear fit parameters are here. So you can see that we get the slope out of it. We get the intercept, which is up here on the line, right, in the trend line. We get some error factors. Don't worry about those. R squared, don't really have to worry about those. F statistic. The thing that is useful is the standard deviation of y. And that just means the standard deviation, the spread, right? That means the spread in the values in y, right? So that and y here is our are the x values, right? So that's the vertical axis is in x, even though it says standard deviation of y. That just means like whatever is on this vertical axis. So this standard deviation is useful because it tells us the spread in the values of x, right? Okay, so that's helpful for estimating error. All right, so what's the basic idea? So what we want to do is we want to calculate the average velocity, right? So we're going to be calculating the average velocity. Oops, can't spell. Average velocity, which is going to be the total travel distance, right? Delta x over the total time. And if we come over here, we can see that the total distance is going to be this final value, 22.2 minus this initial value, right? So if I do that, let's come over here and say for our case here, this is going to be 22.2 meters minus negative 0.25964. I should probably cut that off, over delta t. Well, what's the total delta t? Well, it's 4.6 seconds minus 0 seconds, and so it's just 4.6. Okay, and if we look at my Excel spreadsheet over here, I calculate the average velocity here by taking, and I take x over t, right? But what I'm doing, you can see over here, is B48. So B48 minus B2, right? This is what we do on the equation over there. Let me make this a little smaller so you can see it. Okay. So, and then over A48 minus A2, which is 0. Didn't really have to do that. And I'm rounding it. This is what this round function does in Excel. Just helps me round things easily. And this is what I get, 5. Okay, now I want to estimate the error in that calculation. So this we get 5, right, for this, meters per second. Okay, this does not need to be that big, I don't think. There we go. So we can just a little bit more. Okay, there we go. Okay, so now I want to figure out what is the error in this calculation. All right, so we're going to use something called propagation of errors, and it's really quite simple when you get the hang of it. And what it does is it allows me to figure out what is the change in the average velocity when I account for error in x, and what is the change in average velocity when I account for area and time. And then I combine those two errors in quadrature, right, as you'll see, to get a good estimate of the error in the average velocity. Okay, so it's a kind of a mouthful. So let's see. So let's first look at what is the error in x. So I have here the actual distance that the object traveled, and I'm just going to write that down here. I also calculated that too. So this thing, 22.2 minus 0.25964 is actually 0. Hold on a second. It's not 0 anything. It's 22 right here. You can see it right here. Let me just erase that because I just wrote down the wrong thing. Silly. Right. Here we go. And I'll get my pen back. Hello, pen. There we go. All right. So it's right here. This whole thing is 22.45964. I'm not dealing with significant digits or anything right now. Just writing numbers down. And that's meters, and of course over the 4.6 seconds. Okay, so I want to know what is my error in X, and we just looked at that, right? We just saw that the standard deviation is kind of a measure of the spread. Now you can see, because these lines, if we look in Y, what do we see? We see this one's here, this one's way up here, this one's here, this one's way down here, right? Kind of scattered along this trend line. And this tells me that the measurements have some error in this vertical direction, right? The error in X. There is error in X. If there weren't, right, then I should get everything right on a trend line, work perfectly on a line, but I don't. So there is X. So think of it like you're taking data, right, and you're taking some data, and there's some errors in there when you're taking it, so you're not quite going to get right on the line, right? So this one should have been on the line, but it's not. This one, well, it's way above the line. So I'm using the line as my good guess for what is a perfect measurement. Okay. So there's some spread here. So if I look at the standard deviation in Y, that tells me how spread out it is. And if I use 2 times that, that's like the 90% confidence interval, right? So here is where I did that. You can see from my formula here that it's just 2 times F36, which is this guy, F36, rounded up. Okay, so this is a good, it's an estimate of what of my 90% confidence interval. Okay, so if I do that, right, so this guy here is, we said was 5, right? So let's write that down again. So my average velocity has some error because this has error, and it has some error also because this has error. Okay, we want a plus or minus something here, right? That's what we're after. All right, but we do know that if I say that X, right, that delta X, the total distance traveled is 22.45964. Again, I'm not dealing with significant digits right now. And then we have with 90% confidence interval of, 2, right? And this was 2 times, rounded version of 2 times the standard deviation in Y. All right, what about time? Well, that's harder because I have no way to know what the spread is in this position because it's exactly 0.1 every single time. So, and I didn't do this experiment, right? Remember, we're given this data. You didn't have a stopwatch where you could be like, oh, well, I wasn't really good at pushing stop, and so I estimate that my error is, 200 milliseconds, right? We don't have that. So I just kind of had to make that up. And again, I did basically a similar thing. I just said, well, let's use 200 milliseconds as our jitter in time. Like, pretend that we took this with a stopwatch and we weren't so good with pushing it at the right time. Obviously, from this data, sure doesn't look that way, right? It looks perfect. But you got to have some estimates. So I'm just making that up, basically. So delta T, we said, was 4.6 seconds, right? This is meters, with a 90% confidence interval, I'm just guessing, of 0.2. So this is completely up to you. Okay. All right. And you could even choose to not include jittering time, right? You might be like, look, this data was given to me at 0.1, 0.2, 0.3, 0.3, exactly. That's fine. That's your decision, right? Totally fine. And this would be 2 meters, obviously, 2 seconds. Okay, and 0.2 seconds. So I have those. So how do I get them? How do I get a measure of how that affects this average velocity? Well, it's pretty simple. I can say, okay, what happens when instead of using just delta x, I use delta x plus 2 meters, right? Well, right, so plus or minus 2 meters, and I'm just going to use plus, so I'm going to say, okay, I'm going to say delta x plus 2 meters over time, where now I'm not including jitter and time right now, I'm just leaving the time alone. I only do one at a time. This minus the actual value, right, delta x over t, delta t, which we know is 5, right, should give me, like, how does this change affect my average velocity? And obviously plus or minus, you're going to get the same number either way. Try it if you don't believe me. And so this, right, is going to be my delta x, which is 22.45964. Anyway, I would do this with Excel, not by hand. But and then plus 2, and that's meters, over 4.6 seconds, and then minus, 22, well, 45964 meters over 4.6 seconds. And that should tell me, what is the change in average velocity. So I'm going to call that delta V average due to x. Okay. All right. And I did that in Excel. If we come over here, so you can see, what do? I take the K42, right? Where's K42? Let's see, here's K42, that's my X, right? Plus M44, which is this, over L42, which is the 4.6, and then I subtract off K42 over L42, right? Which is exactly this thing. And what do I get? I get this. This is the change, and I didn't name that. This says delta V av x, so I named it the same thing. And I get this to be 0.43478, whatever, right? Okay, you can see in Excel. Keeping all the digits just what I'm calculating. Okay, so now this tells me how much would V average change if delta x was off by 2 meters, doesn't it? Now I can do the same thing with the time, delta V average due to the time jitter. Again, maybe you would be like, time really doesn't have any jitter, I'm just not even going to do it. Then this would be your answer, and this would be, sorry, this is in meters per second, and good with my units. This would be your answer for the for delta V average, right? That would be it. Of course, you would round it to the right number of significant digits, but I'm just pretending that I know there's some jitter in time. And now what do? Well, I want to substitute in, instead of just delta t, I substitute delta t plus 0.2 seconds, okay? All right, so what do? I just say, oh, okay, so this is just regular delta x over the delta t plus 0.2 seconds, right? That's my jitter. And so I get the 22, delta x is 22.459 ... meters. I'm just going to put truncate it because really I'm letting Excel do all these calculations. And then delta t, if we look at delta t, what is delta t? Sorry, it's 4.6. And of course it's plus or minus, but we use a plus just to see what happens. All seconds, right? And what do we get? Well, and then of course, oh no, boy, I just left off something. Don't do this. We need to subtract off, right, the value that doesn't have a jitter in time. So that's just delta x over delta t. Oh, minus delta x over delta t, just like we did over here, right? Just like we did here. We do that here. Sorry, I just left that off. Should be a minus sign. And then delta t. So, and remember, this is just this stuff. And if we go over here, you can see my Excel calculation here, right? If I go to here, you can see we have K42 again, which is this, over L42, which is this, plus M47, which is this, minus K42, which is just the delta x, over L42, which is just the delta t, and we get this value minus 0.2034 ... meters per second, and that is our delta V average if you change t. And to combine these two errors together, you do them in quadrature. That's what it's called. So delta V average, so that this change in the velocity due to these two errors, you add in quadrature. So that means the square root of this error squared plus this error squared. So delta average x squared plus, yeah, I can't write apparently. Hold on. That's supposed to be delta V average. Delta V. So delta V average from the x thing, the x change, plus delta V average due to the t change, right? T is error. And you square those two, and you can see I do that here in my combined error, right? Delta V av, the square root of this thing squared plus this thing squared, right? And I end up with just 0.48 meters per second. I'm rounding, obviously. Okay, so this, right, is the combined error. And I would round that up to one significant figure, i.e. 0.5, okay? And that's here, okay? So here we have the combined error. So that means that if I were going to write delta V average, it would be V average is equal to 5 meters per second plus or minus 0.5 meters per second, right? Because that's what this guy was. We rounded up to one significant digit. And that's how you combine errors. So, and it works for everything. That's the beauty of this method. So if you had some complicated function, right, instead of just delta x over delta t, you had some complicated function, you just substitute the error into that function just the way we did here to get the contribution of that particular variable's error, right? And then you do it again. And then if you had 3 different things, you would add 3 different things in quadrature to get your total error. Okay, so again, notice that if I decided that my t did not have error because it seems dumb, which I agree it probably does seem dumb in this case, then look at what would have happened, right? I would have calculated delta V average, just normal, and gotten this. And then when I add in quadrature, there really is nothing to add. This would not be here. And this would be delta V average x squared square root, so just delta V average x. And I would have gotten this for, right, rounded to one significant digit, which would have been 0.4. That would have been my error. So it's really up to you. I just did it, with t because I just wanted to show 2 variables, really, honestly, because there's no good reason to use a t. So that's kind of up to you. I hope this helped, and let me know if you have any questions.